In this video, we prove the validity of the algorithm to compute the inverse of a matrix. In the first video about invertible matrices, we gave the definition of an inverse. We also saw that an invertible matrix has a pivot in every row and every column, so an invertible matrix has to be square and should be row equivalent to the identity matrix. In the previous video, we've seen an algorithm to actually compute the inverse matrix if it exists. If A is row equivalent to the identity, then the super-augmented matrix with A on the left and I on the right can be row reduced to I on the left and some other 3x3 matrix. This right-hand side matrix is the inverse of A. But why does this work? Recall, when we set up our algorithm, we actually constructed the matrix C such that A times C is equal to the identity. To show that C is the inverse of A, we need an additional property. C times A must also equal the identity. We will show that in this video. Once we know that both products of C and A are equal to the identity, we can conclude that C is indeed the inverse of A. To be able to analyze what is happening, we rewrite the row reduction process in terms of elementary matrices. This will enable us to use the rules of matrix multiplication to gain insight in what is happening. Every step of our row reduction can be regarded as a left multiplication by a 3x3 elementary matrix. First, left multiply the augmented matrix by elementary matrix E1 to denote our first row reduction step. Then multiply by E2 for the next step, and so on, and so on, and so on. Eventually, after some k row operations, we obtain the reduced echelon form. I on the left-hand side, some matrix C on the other hand. Let's study this final row equivalence in terms of elementary matrices. We can derive two expressions. Ek times Ek minus 1 times Ek minus 2 all the way up until E2 and E1 times A must be equal to the identity matrix. And Ek times Ek minus 1 all the way up until E1 times I equals C. Now combine these two expressions and you see C times A equals a bunch of elementaries times I times A, which is just the blue expression all over again. And that's the identity. So here we have it. C times A equals I. So as promised, A is invertible with inverse matrix C. So indeed, our algorithm does it all. Test for invertibility and compute the inverse if possible. And as a bonus, we see that the matrix A is invertible exactly when it is row equivalent to the identity. In the last couple of videos, we have discussed inverse matrices. We now know what an inverse matrix is, which matrices are invertible, and how to find their inverses. Good luck!